Modern conventional farming treats crop nutrition like a mathematical equation. You calculate desired yield, measure the dirt, and pour in the corresponding chemical formula. That formula almost always relies on nitrogen, phosphorus, and potassium. Walk into any farm supplier and you'll find these three letters, NPK, marketed as a complete diet. But these represent exactly 3 of the 17 essential elements plants require to complete their life cycles. This biological periodic table shows the scale of the deficit. We aggressively apply N, P, and K, while the secondary nutrients and trace minerals, elements like calcium, magnesium, and zinc that serve as the spark plugs for plant metabolism, fade into the background. Agronomic data reveals that modern high-yielding crops strip more secondary nutrients like calcium, magnesium, and sulfur from the soil than ever before. Yet these specific elements are almost entirely absent from standard synthetic fertilizer programs. Without adequate calcium, cellular walls lack structural integrity, leading to blossom end rot in tomatoes and hollow heart in potatoes. When a crop lacks zinc, it loses the ability to form essential growth hormones. Relying strictly on an isolated NPK input forces the crop into a state of biological starvation. The plants may grow quickly, but they remain structurally weak and metabolically compromised. The problem compounds when we look at soil chemistry. Chemicals in the soil do not work in isolation. Adding a heavy dose of one can physically block a plant from absorbing another. This is known as nutrient antagonism. This chemical flow chart demonstrates the lockup occurring in a standard commercial application. A farmer applies a high concentration of synthetic phosphorus to push root growth. As the synthetic phosphorus floods the system, it immediately binds with available zinc. This chemical reaction creates a new compound the plant cannot absorb, instantly inducing a severe zinc deficiency. This deficiency limits the plant's ability to use nitrogen, causing the leaves to turn yellow. The typical response is applying more synthetic nitrogen. This sudden influx triggers a massive metabolic demand for magnesium. But because magnesium was never added, chlorophyll cannot form. The entire biochemical system crashes. This antagonistic cascade traps the farmer in an expensive cycle. Adding one chemical creates a deficiency in another, necessitating further synthetic inputs to chase symptoms. Breaking this cycle requires a shift in engineering, moving away from feeding the plant directly and focusing instead on the soil food web. In natural ecosystems, plants do not passively wait for nutrients to arrive. They actively source them through a microscopic underground system known as the exudate economy. Through photosynthesis, a plant produces simple sugars. It then deliberately injects 30 to 40% of that carbon straight down into the soil. This massive carbon investment is designed specifically to attract bacteria and fungi, the primary miners of the soil food web. The microbes consume these carbon sugars for energy. In return, they begin synthesizing and releasing highly specific organic acids and enzymes. These microbial enzymes act as a biological solvent. They dissolve the tough crystalline structures of the raw sand, silt, clay, and rock particles that make up the soil. By breaking down these mineral structures, the microbes extract elements like iron, calcium, and phosphorus directly into their own cellular bodies. The plant is literally farming its own microscopic workforce, trading carbon energy to microbes capable of mining precise nutritional elements from inert dirt. Mining the minerals is only the first step. At this stage, the extracted nutrients are trapped inside the microbial bodies and remain unavailable to the plant. Generating plant-available nutrients, specifically nitrogen, relies on a highly precise predator-prey dynamic at the microecological level. Look at the biological structure of the prey. A standard soil bacterium maintains a rigid internal carbon-to-nitrogen ratio of exactly 4:1. Now enter the predators, protozoa and nematodes. These organisms have a different biological requirement. A nematode requires a carbon-to-nitrogen ratio of roughly 5.9:1. When the nematode grazes on bacteria, a mathematical mismatch occurs. The predator is consuming far more nitrogen than its own cellular structure can process. The nematode cannot store the excess, so it excretes it. That nitrogen is ejected directly into the root zone as ammonia, which is instantly available for the plant to absorb. This process scales massively. Research shows that protozoa and bacterivorous nematodes performing this extraction contribute approximately 30% of total net nitrogen mineralization in many ecosystems. The effect isn't limited to nitrogen. Studies demonstrate that the presence of healthy nematode communities increases net phosphorus availability by 23%. Biological nutrient mineralization is a predictable, mathematically rigorous engine. When the full food web is present, it provides the foundation for a self-sustaining system, significantly reducing the reliance on external chemical inputs. Beyond the immediate root zone, the soil requires a transport infrastructure. This is built by mycorrhizal fungi. These specialized fungi form a direct physical relationship with plant roots. They grow outward, weaving through the soil to scavenge nutrients and water far beyond what the plant could reach alone. In exchange for carbon, these fungal networks deliver up to 70% of a plant's phosphorus and 40% of its nitrogen. As these fungi weave through the earth, they secrete a sticky, protein-based glue called glomalin. Glomalin binds loose soil particles together into stable macroaggregates. This biological engineering restructures the physical hydrology of the earth, creating the porosity required for air and water movement within the soil profile. Looking at a cross-section, the contrast is stark. On the left, synthetically managed dirt lacks biology. It collapses, compacts, and repels water. On the right, biologically aggregated soil operates like a sponge, allowing deep root penetration and rapid water infiltration. Mycorrhizal architecture does more than feed the plant. It physically engineers the earth to prevent chemical runoff and build extreme drought resilience. Harnessing this biological engine requires a shift in practice. Farmers must stop destroying the underground infrastructure they need to yield crops. Every pass of a mechanical tiller violently shears through fungal networks. It shatters the macroaggregates, exposes organic matter to rapid oxidation, and kills the organisms attempting to cycle nutrients. The biology depends on a constant food supply. Bare soil and a lack of living roots means the carbon pump is effectively shut off. Continuous cover cropping solves this by keeping diverse, living plant species in the soil year-round. This ensures the carbon investment reaches the microbial biomass even between cash crop rotations. High-quality, finished compost further supports the system as a complex food source, inoculating the soil with billions of beneficial organisms ready to process raw organic matter. Modern agriculture reaches its peak efficiency when the farmer shifts from chemical oversight to the precise management of microbial habitats. Biologically active soils sever a farmer's reliance on expensive synthetic inputs. When the soil food web handles nutrient cycling, overhead costs decrease and profit margins grow. Crops grown in these complex biological webs absorb a complete spectrum of micronutrients. They yield heavier harvests with higher Brix levels, delivering superior human nutrition. Below ground, fungal networks sequester massive amounts of carbon, while the aggregated soil structure protects local waterways from toxic agricultural runoff. ವೈಜ್ಞಾನಿಕ ಸಾವಯವ ಕೃಷಿ ಪದ್ಧತಿಯ ಬಗ್ಗೆ ಇನ್ನಷ್ಟು ತಿಳಿಯಲು ಈ ವಿಡಿಯೋ ಲೈಕ್ ಮಾಡಿ, ಶೇರ್ ಮಾಡಿ, ಕಮೆಂಟ್ ಮಾಡಿ ಮತ್ತು ದಿ ಜೆಪಿ ಆರ್ಗ್ಯಾನಿಕ್ ಫಾರ್ಮ್ ಚಾನೆಲ್ಗೆ ಸಬ್ಸ್ಕ್ರೈಬ್ ಮಾಡಿ. The mechanisms of the soil food web have been refining crop nutrition for over 450 million years. Aligning with this biological reality is the only economically and scientifically sound path forward for agriculture.